This is part 2 of day 24 of Advent of Code 2020. And in this part, we have yet another sort of variation on Conway's game of life. What we'll be doing here is, given our set of tiles for this layout of the lobby, we're going to, after we figure out the black and white placement of all of them, we're going to go through and determine whether each day a tile should be flipped from black to white or white to black, or whether it should stay on the side that it's in based on these two rules here. So again, this is sort of reminiscent of Conway's game of life, except instead of a square grid, we're dealing with a hexagonal grid. And so instead of having 8 neighbors, each tile will have 6 neighbors. And yeah, let's see. The black tiles, if they have 0 or more than 2 black tiles as neighbors, then they'll be flipped to white. Otherwise, they'll stay the same. And then with the white tiles, anytime they have exactly 2 black tiles immediately adjacent to them, they'll flip to black. As usual with Conway's game of life, we apply the rules to everything on the grid as it is on a particular day, and then perform the flip simultaneously. So it's not like the results are affected as things are processed in line or anything like that. Yeah, so in the example above that we were given, if we let it run for 100 days, we'd end up with 2,208 tiles facing with their black side up. And we have to take the input that we were given and run that for 100 days and see how many black tiles we end up with that are facing up. Yeah, so there's a couple things going on here. I think first we get to reuse most of our solution from the previous example. But then from there, we need to do some work to figure out which tiles are our neighbors. And I think we can create sort of a set of translations from a given tile's position to figure out its 6 neighbors. Since we've been tracking just which tiles are black, we'll have to also come up with a scheme for, we're going to want to figure out which white tiles we need to pay attention to. We're dealing with sort of an infinite grid or, space here. So we are not going to want to consider everything. So I think we'll have to leverage what we know about the positioning of black tiles to figure out which white tiles we need to pay attention to, since it's just white tiles that are having black tile neighbors that we need to think about doing any flipping with. And then I guess the last piece is then running that for 100 days. Okay, so I guess I want to jump over here again and just notice that if we have a given tile with an X, Y, and Z coordinate, we're always subtracting and adding 2 of the 3 coordinates from the current position to get one of the 6 neighbor positions. So we can just kind of keep in mind what we're seeing here as we create a coordinate translation algorithm in our solution, which we'll start working on over here. So I'm going to save this as part2.rb. And yeah, I guess while I'm thinking of it, I'd like to create this method for giving me all of the neighbors for a given position. So I'll say neighbors determine, neighbors is fine. Neighbor positions, I guess. That's what we're going to be getting. And so we'll be given an XYZ And so from that, we're going to say, yeah, what were the different ones? It's like we always have a 0, then we have a +1 and a -1. Then we have a 0 and a -1 and a +1. Then our 0 can be here now. So we'll have +1, -1, and then -1, 0, +1. So we're going to call these our translations, and then we just got 2 more to go, so we'll have +1, -1, 0, and then lastly -1, +1, 0. Awesome. And yeah, I guess what we want to do is just come in here and we want to place x, y, z, and then x, y, z, x, y, z, so on and so forth. Oops, x. Okay, so yeah, these are ultimately not our translations anymore, but just the neighbors. And so that's the array that this method will return. Cool. So that's helpful to have that out of the way. Yeah, because I think that's going to come in handy both for just determining for a given tile what its neighbors are, and then also for saying, okay, we've got a black tile, what are the potential neighbors of that black tile that we need to consider as we know we need to be looking for white tiles that need to be evaluated. Cool. So yeah, that's in place. I guess I want to double check that. Let's see. I'm wondering if if we run all of our program that we did from part 1, and then we use sort of that initial state as the seed for like day 1 then. So does it say that? Yeah, it's meant to be a living exhibit. Day 1 is 15. So it's like before day 1 we had 10. I mean that's what it started as. So maybe those turn into 15. Yeah, this must be a starting point because otherwise everything's white and then nothing is going to change. Okay. I've reasoned myself through it and we'll proceed. So deleting some of that. So we come out on the other end here and we've got tiles. And that's sort of our starting set of tiles. And this is the thing the hash that we're gonna be working with as we process each day. So we'll do 100 days times. Keep an eye and just puts out day I+1 just to see the progress as we go. And we will need to, I guess, start off by process all black tiles from the tiles hash. Keep a list of white tiles to process. and process all listed white tiles. So we'll do that 100 times, and then I think this little bit of code here for counting the number of black tiles is going to be the same. Yeah. So I guess in that case, if tiles tracking if the current side is, I mean, you get either black or nil, and so then if current side is equal to nil, yeah, I guess current side gets set to black if current side up dot nil. So that was, maybe shouldn't be refactoring this piece of the code right now while I'm got the rest of this in flux, but what I'm going for here is saying I don't really want to track the white tiles anymore. I just want to track which tiles have been flipped to the black side. Sort of the absence of a record or an entry in this tiles hash will indicate that it's white. That'll just give us less to keep track of. Yeah. So let's grab the rules from over here because we're going to need to start applying these pretty soon. Oops. Okay. I'm going to comment those out. And yeah, those, we'll just keep those in mind as we go. So for tiles.each do, we're going to get a position and a side, and presumably these sides should just all be black, but might be worth hanging on to that variable just in case. And then I'm going to want to, I guess, keep track of white sides, white tiles to check. I'm going to use a set here because the set will allow me to not deal with duplicates. Because you could imagine that as I'm, let's say this tile is black, so then I notice that maybe most of the tiles around it are white, and then this tile is black, so maybe these two are white. Then for both this tile and this tile, we'd register that these are some white tiles that we need to do a check on, and we don't want to record them twice as we're processing all the different black tiles. So we'll use a set in order to make sure we're only recording these once and checking them once. So that's kind of the reasoning there. So white tiles to check will just be a set of positions. So it'll be, set something like, X, Y, Z, 2, 3, so on and so forth. Like that. Cool, so process all the black tiles. Neighbor positions for position. So that's going to be, this is coming as a hash, and this is going to splat that out. I don't actually think that's going to do what I want it to do, so I'm just going to say position X, position Y, position Z. Okay, and so we'll get neighbors back, and then for each of the neighbors, we're just going to want to check whether it's contained in tiles. Yeah, so neighbors.each neighbors.count, I guess. And we'll get a neighbor position. And we'll want to check if tiles neighbor position equals black. And so I think this whole thing can just be tagged onto here. So we'll create a new line. New line. Okay. So we don't need neighbors then. So we'll count that. We'll get the we'll get some sort of count here of the number of the black tile neighbors, and if that's 0 or if it's greater than 2, then we need to remove this from the tiles hash. Yeah, okay. So let's say tiles position gets nil if black tile neighbors equals 0 or black tile neighbors more than 2, so greater than 2. Okay, otherwise we just leave it alone. And then while we're doing this, I think we also want to register these tiles in the white tiles to check set. So yeah, how are we going to do that? This is probably not something you generally want to do, but I'm going to do a bit of side effect inside of this count. So we'll get tile side so paste that in there so that we'll pull the tile side out and we'll return tile side compared to black. But if the tile side is nil, then we want to, if that's true, then we want to, that means it's a white tile, so we want to add it to the tile check. Like that. Okay. All right, so that will update this set that we have. So then down here, we'll want to process this set of white tiles. So we'll say white tiles to check, each do, and it's going to look pretty similar to the above, where we're going to say, yeah, give us the neighbors. And then we don't need to do this extra stuff this time. Tile side, whoops. Now we'll want to do neighbor position of, right, like that. Yeah, pull it out of tiles, compare it to whether it's black or not. And then if it is, that gets our count. And then I'll have a similar line to this. But the rule is any white tile with exactly 2 tiles immediately adjacent to it that are black, we'll flip it. So tile position gets black if if that's nil. Or sorry, if that's exactly 2. Okay, so this will, yeah, I guess process all the black tiles, all of the white tiles that are adjacent to black tiles, and then we'll do that 100 times. And we'll get out the other side with an answer that we can see if, yeah, an answer that we can see if it is what they're looking for. Let's start with sample then. That way we can get a point of comparison here. Do part 2 and uninitialized constant set. Why is that? Do I need to require set? That doesn't seem right. Ruby set class. I suppose we do. Okay. Good to know. Let's give that another try. Undefined method X. Oh, sure. What line is that? Line 70. So I think we need to do hash access instead of, yep. Oops. See, close that, and then we'll copy that line down to here. Okay. And we'll give it another run. Conversion of symbol into integer, line 81. Okay. Oh, right here. Position. Oh, sure enough. This is a set of these things. Or, right? What are... Am I sticking in here again? Oh yeah, not quite like that. So what I'm trying to put in this set is sort of like X, Y, Z. So I think that's what should be coming out here. Is it just that extra argument that was throwing it off? No, it still thinks conversion of symbol into integer. 81, okay. Let's pry in here and see what we're looking at. Oh, these are arrays of positions. Okay. Great. That's good to know. So that I can splat like this. And that's not going to fit there, so I'm going to have to, Shoot, made this a little more complicated than it needed to be, but that's okay. Pass that in like that. And then here we're actually going to have to say X gets X, Y gets Y, and Z gets C. Okay. And we're coming out the other end with 0. That's not at all right. X, Y, Z. Okay. Well, let's come out here and make sure my refactoring from earlier didn't bust anything. Tiles dot just tiles, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15. 15. Is that right? It should be 10. So, crud, what did I do wrong here? Do we have any duplicates in here? No? Yeah, I mean, I think I got something wrong here because we should be coming out at the beginning of this with 10 tiles that are black. So the fact I'm coming out with 5 is a problem. Let's exit out of here. And let's see. So if oh, I see. I need to set it back to nil. So if current side up is nil, set it to black. Oops. Set it to black. Otherwise, set it to nil. Now let's pry in there, and I bet we get 10 instead of 15. Or not. Huh. I wonder what I've done to track in position 2H, yeah. Let's take a look, tiles. Are seeing the same thing? Oh, okay. But yeah, they're set to nil. Okay, that's fine. Okay, in that case, I need to say next if side nil. Okay. So let's run this whole thing. Let me get rid of the pry first. There, I think I fixed whatever was going on here. We're still getting 0. Oh, well, we're updating it inline, so that's going to be a problem. Jeez. Okay. Next day's tiles, I guess. Okay, and then after all of this is said and done, tiles gets overridden with next day's tiles. And we're still getting 0. Huh. Why is that? Next day's tile starts at empty. We update it with position for each one. I guess we don't want to put nil in. Oh, right. Jeez. Okay, so next day's tiles, position gets black if black tile neighbors is greater than 0, and black tile neighbors less than or equal to 2. And we don't want that. I see. That was the mistake there was that I was not adding the positions of black tiles to this next day's tiles thing. I was just inserting the sort of reverse of that, which is when they were nil. And so then that was throwing off the whole process. And we're still getting 0. Huh. Each time I fix something, I'd end up back in a position like that. I'd be curious to see what we're seeing in here. So we get in there, say, yeah, what do we have available here? Black tile neighbors, 0. Position. Okay, and then neighbor positions for position X, position Y, position Z. Does that look right? -3, increase by 1, decrease by 1. Okay. -3, 0, 3. Yeah, I think these are all right. Let's see, tiles. -3, 0, 3. I mean, that we should be coming out with at least 1 here. -3, 0, 3. That lines up with -3, 0, 3. But where am I? Why are we coming up with 0 for tile neighbors? Yeah, that doesn't seem right. Each count, I guess, and the count was oh, the positions are going to come out as arrays. Oh, bummer. Okay. Instead of a hash, so then we're not going to be able to look it up. I see. So, I guess position array to hash, I guess it's X, Y, Z. X, Y, Z. Not sure if it was worth peeling out this method, but we'll try it anyway. Oh yeah, that'll be good. So I'll say position hash gets, what did I call this up here? Position array to hash. Okay. Position array to hash with the neighbor position hash splatted out. This position hash is what we'll peel out of there. It's also what we're going to put in the white tiles to check. So now we're going to be actually checking something. And then down here, white tiles to check. We're going to be dealing with a position hash now. And so then, let's see, we're going to have to update this again to be back to this form. And yeah, each of these is still going to have to do this thing. Okay. And then the position can just go in like that. Position. Okay. I think I've updated everything. Let's get rid of this pry and see if that gets us towards an answer. We're actually doing some checking now. 1432. I don't think that's quite right. That was interesting though. Yeah, I gotta, I guess, step out from the problem a little bit and think, what is it that's not going according to plan? I mean, all of this initial logic seems like it ought to be right. This neighbor positions stuff seems good. 1, 2, 3, 4, 5, 6. But there could be a fault in it, like that Z right there. Wow. Okay. That's rather frustrating. $22.08. $22.08. So then what happens if we run it on the regular input? I'm worried about how slow this is going to run. Oh, not too bad. Ooh, starts to crawl at the end, but we're going to get there. 42.25. And is that going to get us a gold star? It is. All right, well, we've completed day 24 with our second gold star. Thanks for watching.